Hello students, and welcome back to another geometry video. You know what to do. Pause the video and try this problem in your notes, and then unpause it to do it with me. Alrighty, we want to find the coordinates of the circumcenter of the triangle with the given vertices. So step one is let's see what triangle we're working with here. So I have -1, 4 is W, +1, 4 is x, and y is 1, -6. So our triangle looks something like this. That side was a little slanted for my taste. There we go. All right. So next, I have found the triangle. Now I need to find the circumcenter. So, in order to do that, I need to construct the perpendicular bisectors of the sides of this triangle. So, let's look at the vertical and horizontal sides, since I know what's perpendicular to those. I know that a vertical line is perpendicular to a horizontal line, and I know that a horizontal line is perpendicular to a vertical line. So let's take side WX, we'll take the top side, and we'll find the midpoint, which isn't too bad for this since the points are, 2 boxes away. So we're just at the only box that is in between W and X, which is 0. And now I just draw my perpendicular bisector. Awesome, that wasn't bad. Now let's look at side XY. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means I should have 5 boxes on either side. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, so I'm going to draw a horizontal line at the midpoint of this side. And where do they meet? Actually, let's get green. It looks like they meet right here at 0. This point is 0, -1. There you go. And remember, I don't need to find where the third side's perpendicular bisector is, because I know that all of the perpendicular bisectors are concurrent at the circumcenter. So if I find 2, the third one's going to go right through that point as well. So I only need to find 2 of the perpendicular bisectors. Wonderful! Thanks for doing that with me. Let's move on to what we have for today. Today, we start section 6.3, which is about medians and altitudes of triangles. Now, we're not going to do any problems with altitudes of triangles, but I am going to show you what they are and what they're used for. But there are not too many applications of altitudes and orthocenters, so we're not going to talk about those a ton. But medians, on the other hand, oh boy. These are incredibly important. You'll talk about these in physics. Well, not medians. So, hang on. Our learning target for the day is that you know what medians and centroids are. So these work together, and centroids, you'll learn about these in calculus, calculus 2. You'll learn about these in physics. Centroids are incredibly, incredibly important because it has to do with the center of mass, which is very, very important when you want to hang art from the ceiling or when you want to launch a rocket into space, things like that. So centroids are incredibly important, and we're going to spend a majority of this video talking about centroids. Another part of the learning target is that you know what altitudes and orthocenters are. Now, orthocenters are less interesting. There are fewer applications, and honestly, it's very difficult to find applications of the orthocenter, which is why we're not going to talk a lot about it. And our success criteria is that you can use medians to find the centroid, and that you can use the centroid to solve problems. So our main focus for this video is medians and centroids, with a little bit of altitudes and orthocenters mixed in. Alright, so first we are going to talk about medians and centroids. At the last, like towards the second half of the video, we'll start talking about altitudes and orthocenters. So what is a median? We hear about it in driver's ed, but what is it in math? So a median of a triangle is a segment from a vertex, which means from a corner of a triangle, to the midpoint of the opposite side. So if you want to create a median, what you need to do is you need to find the midpoint of one of the sides, just like that's what D is, and then all you have to do is you connect that point to the opposite corner, and that's a median. So if you can find the midpoint, you can make a median. Awesome. So yes, BD is a median of triangle ABC. Now, why do we care about medians? Because if we construct all of the medians, the point of concurrency of the three medians of a triangle is the centroid. So if you want to know what the center of mass of this triangle is, you just need to construct all of the medians, and wherever they cross, that is the center of mass. So if I took this triangle and I put it on the tip of a pencil, right at this point, it would balance on the tip of that pencil. So it's a fun party trick for your friends. Okay, so median is from the midpoint to the opposite vertex, and when we make all of the medians, we find our centroid. Now, why do we care about centroids? We care about medians because we can find the centroid, but why do we care about centroids? Because it's the center of mass. Also, there is a very, very interesting property of centroids, which we're going to talk about in this theorem, the Centroid Theorem. So, it says the centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. Now, that can be hard to wrap your brain around at first, so I like that they put it in math speak down here. The medians of ABC meet at point P, right, at our centroid, and AP is 2/3 of AE. So AP is 2/3 of AE. So basically, we've split up this entire median. You can think of it as being in 3 pieces. 2 of those pieces are in between the centroid and the vertex. The third piece is from the centroid to the midpoint. So this is PE is 1/3 of AE, and AP is 2/3 of AE. And this is true for every single median. So BP is 2/3 of BF, of the entire median. CP, which is the distance from C, the vertex C to the centroid, is 2/3 of CD, of the whole median. So we can use this to solve problems. We can use this to find centroids, which both of those were in our success criteria. It is also important to note that the centroid is always inside of the triangle. Because we're taking the midpoint of a side and connecting it to the opposite vertex, there is no way that any one of those could go outside of the triangle. So the point of concurrency, or the point where they all meet, there's no way that that could be outside of the triangle. So centroid is always inside of the triangle, which makes sense, right? Your center of mass can't be outside of your body. The center of mass has to be within the object, so that makes sense. Alrighty. Let's move on to our first example where we're going to use the centroid of a triangle. We're going to use the theorem that we learned about in the last slide. So, in triangle RST, point Q is the centroid. So let me get a different color. Point Q is the centroid, and that is important because that means now we can use this centroid theorem. So, SQ is 8, and they gave that to us. Find QW and SW. Okay, so let me color code. I'm a color coder. QW is this chunk, and SW is the whole segment. Okay, so SW is the entire median. The entire median. And what was SQ? So SQ is 8. It's from the vertex to the median. Or excuse me, not to the median, from the vertex to the centroid. And wait a minute. Don't we have a theorem that says the from the vertex to the centroid is equal to 2/3 of the entire median. So, from the vertex to the centroid, so SQ is equal to the entire, to 2/3 of the entire median. So from the vertex to the centroid is 2/3 of the entire median. So SW is the entire median, so, and SQ is from the vertex to the centroid. So I know that SQ is 2/3 of the entire median. And this is the centroid theorem. We got this from the centroid theorem. Now, this is helpful because I know what SQ is. SQ is 8. So 8 is 2/3 of the entire median, and I don't know what SW is. I'm trying to find what SW is. So 8 is 2/3 of what? How can I solve this equation? Well, remember that when I have a fraction times, whatever I want, a fraction times a variable, I can multiply by the reciprocal. You'll remember the reciprocal from section 3.5 because perpendicular lines have negative reciprocal slopes. So the reciprocal of 2/3 is 3/2. So I'm going to multiply both sides by 3/2. And look, on the right side, when I multiply by the reciprocal, the numerator cancels with the denominator, right? 2 is on the top and the bottom, so it cancels. And 3 is on the top and bottom, so it cancels. So on the right side of my equation, I just have SW. Now, I just need to figure out what 3/2 times 8 is. So I can do, 3/2 times 8/1, which is 3 times 8 is 24/2, and 24 divided by 2 is, is 12. So SW is 12. So, and I'll color code that. The entire median is 12 units long. They didn't tell us units. We don't know if it's inches or feet or whatever, but the entire median is 12 units long. Are we done? Not quite. Remember, they also wanted us to find QW, and QW is this bottom piece. So if we get rid of the purple was the entire median. QW is the other side of the median. So SQ was from the vertex to the centroid. Now we want from the centroid to the side of the triangle. So there's multiple ways that we can do this. One is we know that QW is 1/3 of the entire median. So we can do that, and 1/3 of 12. Oops. 1/3 of 12 is 4. That's one way that we can solve this problem. Another way is I know that the entire median is 12, and I know that the other part of the median is 8. So if I do 12 minus 8, I get 4, and QW equals 4. So if using the segment addition postulate is easier for you, and you'll remember what we did right here was back in section 1.2. So if that is easier for you, by all means, you can do it this way, and if this made more sense to you with the centroid theorem, you're more than welcome to do it that way as well. All right, let's check and see if we were correct. Let's see, SQ is equal to 2/3 of SW, that's the centroid theorem. Substitute 8 for SQ, multiply each side by the reciprocal, and 12 equals SW. And yes, so they used the segment addition postulate to get 12 minus 8, which is 4. Which we did it that way, we also did it another way. But yes, either way, we are correct. Woohoo! All right, now we're going to move on to example number 2, which is asking us to find the centroid of a triangle on a graph. So, just like last time, our first step is to graph the triangle. Graph the triangle that we're trying to work with. So, R is at 2, 1. S is at 5, 8. And T is at 8, 3. Oops. Trying to make as straight of lines as possible. There we go. All right. Now, step number 2 is going to be construct or make the medians. Now, let me ask you a question. How many medians do I need to make? So we know that the centroid is where all 3 of the medians meet. It's the point of concurrency of all of the medians. But remember, in 6.2, in the last video, we only needed to find 2 perpendicular bisectors, because we know that the third one is going to go through there. So do I only need to find 2 medians? Well, maybe I can only find 1. Because I know that if I find one median, I can find the centroid using the centroid theorem. So I really only need 1 median. I could make 2 and just find where they cross, or I could make 1 median and use the centroid theorem. And sometimes it's going to be the easiest to do that. So let's see. Let's see how difficult it's going to be to construct our medians. Because, remember, to make a median, we find the midpoint. Find the midpoint. Connect it to the opposite vertex. So, making medians shouldn't be too bad if we can find the midpoint. So, let's see what is going to be the easiest midpoint to find. Let's see, if I look at side RS, I can see that I have 1 and 8. So the halfway point is 4.5. That doesn't look like a happy midpoint. And of course, I'm just estimating right now. I'm not actually using the midpoint formula to find what these midpoints are. I'm estimating to see, do I want to find that midpoint? Do I want to try to use that midpoint? And it looks like the midpoint of RS is going to be somewhere around here. And that looks messy, so I don't know if I want to use that one. We could if you want, though. We totally could. Well, actually, yeah, let's do that. We'll do this in two ways. So the first way is we'll make two medians. So let's take R and S. So we have 2 and 5. And the y-coordinates are 1 and 8, and we get that the midpoint is at, let's see, 2 plus 5 is 7 over 2, 1 plus 8 is 9 over 2, so yeah, this is not super pretty, but that's okay. 7 divided by 2, this is 3.5, and 9 divided by 2 is 4.5. So we have 3.5, 4.5. So there's our midpoint of side RS, and we'll show that it's a midpoint by using those tick marks. And then I'm going to connect it to the other vertex. Okay. Now we need to find another midpoint. So I'll erase this work here. And let's look at side RT. So R, we have 2, 1 for R, and for T we have 8 and 3. If you forgot how to use the midpoint formula, definitely check out that video from section 1.4. 2 plus 8 is 10 over 2, and 1 plus 3 is 4 over 2. These are some nicer numbers to work with, because 10 divided by 2 is 5, and 4 divided by 2 is 2. So the midpoint is at 5, 2, and oh, look at that. I can just connect it to the opposite vertex. Oh, wow. So that was definitely the easiest midpoint to find and the easiest median to find, because I just got to draw it right along the vertical line right there. Okay, now there's your centroid. I only need to find two medians, right? The third one is going to go directly through there. So the centroid is at 5, 4. 5, 4. And that's where my centroid is. Now, there is another way that we could have done this, because what if we didn't draw this median perfectly? What if we drew it a little bit wrong and it looked like it crossed, you know, what if we curved it or something and it didn't look like it crossed in the right place? I don't know. So there is another way that we can do this problem, and that is if I find one median. So let's get rid of the median on RS, because that one was hard to find. Let's use the easy median that we found. And remember that the centroid, so let's say the centroid is at point C, and we don't know where point C is, but we know that from the vertex to the centroid is 2/3 of the entire median. And we'll call this M for midpoint. So we know that from the vertex to the centroid is 2/3 of the entire median. And, check it out, we can figure out how long this median is. 1, 2, 3, 4, 5, 6. So the entire median is 6 units long. What is 2/3 of 6? Let's see, 2 times 6 is 12, divided by 3 is 4. So this tells us that SC is 4. So if I go from S down to C, I should go 1, 2, 3, 4. And C should be right there. C should be 4 boxes away from the vertex. And where does that put point C? It puts it at 5, 4. Oh, hey! We get the same answer either way. So, you can make 2 medians, or you can make 1 median and use the centroid theorem. It's whatever you are most comfortable with. If you liked the first way we did it, use the first way we did it. If you liked the second way we did it, use the second way that we did it. Either way, let's check and see if we were correct. So they found the midpoint of side RT just like we did, and then they used the centroid theorem. This is the centroid theorem right here. So they did 2/3 times 6, which is 4 units down, so the coordinates are 5, 4. So they used way number 2. Remember, you get to use whichever way that you like best. So, oh, and you can check your answer by using different medians. For sure, I love that. Wonderful. We were correct. It's also worth noting on this slide that it says the median SV was chosen for this example because it's easier to find distance on a vertical segment than it was for our slanted, non-vertical, non-horizontal segment. So that's why they chose to use median SV instead of this median here. Awesome. Okay. Now, we are going to talk about altitudes and orthocenters, but you are not going to be required to do this for homework in my class. Depends on who your teacher is. You might have some homework problems about altitudes and orthocenters, but so I want you to know about them for that reason. Now I'm going to get rid of myself for a second. You can still hear me, you just can't see me, because I want you to be able to see the Spanish if you need it. So, take a screenshot if you need to. I'm going to bring myself back, and boop, magic. Okay, so the altitude is the perpendicular segment from a vertex of a triangle to the opposite side, or the line that contains the opposite side. So when they say, or the line that contains the opposite side, they're talking about this example. And when they say to the opposite side, they're talking about this example. So the altitude can lie inside of a triangle, or the altitude can lie outside of a triangle. If you have an obtuse triangle, your altitude will be outside of your triangle, unless you reorient your triangle. So, it depends on what you're calling your base, and we'll talk more about that in the next slide. Now, so from the vertex, and you drop a perpendicular line. So, drop a line that is perfectly perpendicular. Now, this is not, don't get confused, this is not a perpendicular bisector. So you cannot put those there. Altitudes are not necessarily perpendicular bisectors. They can be. If you have an isosceles or equilateral triangle, they will be. But if you have a scalene triangle, it won't be. All right. So why do we care about altitudes? Well, because the orthocenter is the point of concurrency of the lines containing the altitudes. So if you make all of your altitudes, the point where they cross is your orthocenter. And there are not a ton of cool applications of the orthocenter. There's not a cool theorem about the orthocenter, which is why we're not going to talk about it a ton. So you have seen altitudes before. I wanted to talk a little bit about this, so if you're like, altitude, that makes no sense. Remember, in the area formula for a triangle, A equals half the base times height, you can use any of the side lengths for the base, but the height is the length of the altitude from the base to the opposite vertex. So if you're using this side as your base, this altitude is what your height is. And in this triangle, if you're using this side, if you're using PR as your base, this is your height. So whatever your base is, the height is the altitude from that side to the opposite vertex. So you have seen altitudes before, maybe just disguised in area formulas. All right, so we don't have a fancy theorem, we just have another way of saying that the lines containing the altitudes of a triangle are concurrent. This point of concurrency is the orthocenter. So the lines containing AF, BD, and CE meet at the orthocenter of ABC. And you can see in this triangle, it is very obvious that the altitudes are not bisectors, right? If I look at side AC, AD is definitely not the same as DC, definitely not. So you can tell that altitudes are not necessarily perpendicular bisectors. Not necessarily. And that's important, because sometimes people get them mixed up. Okay, some interesting information. The altitudes do not always intersect inside of the triangle. So your orthocenter is not always inside of the triangle, just like our circumcenter wasn't always inside the triangle. An acute triangle, it's inside. A right triangle, it is on the triangle. And for an obtuse triangle, it is outside. So altitudes are shown in red. So notice that in a right triangle, the legs are the altitudes. And the altitudes of the obtuse triangle are extended. So they took, they took the vertex, dropped the perpendicular line, but they extended it up so that they could actually see where the orthocenter was. Okay, so that's all we're going to talk about orthocenters. I want to show you everything all at once. 6.2, 6.3, this is everything we've talked about in 6.2 and 6.3, and 6.1. So, this first column is how to make the point of concurrency. So you make the circumcenter with the perpendicular bisectors, you make the incenter with an angle bisector, you make a centroid with the medians, you make the orthocenter with the altitude. And they have an example of one of those. So just one median, just one altitude, just one angle bisector. And then in the last column, they show you all of them put together. So they show you all of the perpendicular bisectors, all of the angle bisectors, all of the medians, and all of the altitudes that create the circumcenter, the incenter, the centroid, all of that jazz. And they list the special properties. So for these first three, we had theorems. So this is the Circumcenter theorem, the Incenter theorem, and the Centroid theorem. This last one right here, remember the altitude doesn't have a special theorem. It's just that all the altitudes make the orthocenter. Okay, so if you'd like to take a screenshot of this and write this down, not a bad idea. Not a bad idea at all. If you're like, oh, I know everything on this chart like already makes sense to me, maybe don't write it down, but I'd encourage you to write it down to help you remember. Okay, so now one more very, very interesting thing. And this isn't going to be on any sort of test. This isn't in our book. I just think that this is fascinating. So the centroid, which is in orange on this picture, so when they're talking about the blue and the green, they're talking about this picture over here. So the orthocenter is in blue, the circumcenter is in green, and the centroid is in orange. All of these points lie on this red line called Euler's line. And I know that this looks like Euler, and that's how I pronounced it in high school. It is actually pronounced Euler, and he's a famous mathematician. He's done a lot, especially in geometry. So yeah, you'll probably hear more about him in later courses. So Euler's line has the orthocenter the circumcenter, and the centroid on this line. This line also contains other triangle centers, like the center of the 9-point circle, others but that you don't know about that I don't want to confuse you with, but there are other triangle centers along this line. And this line exists for all triangles. Doesn't matter if it's acute, obtuse, right, scalene, doesn't matter. This line exists for all triangles. And what's even more fascinating is that the relative distances between the triangle centers, so from the blue point to the orange point, from the orange point to the green point, all of the, and from the blue point to the green point, all of those distances are the same. Like the relative distances, no matter what your triangle looks like, and no matter how that line changes and how your orthocenter and your centroid changes, the relative distances remain constant, which is like, how is that possible, right? Because there's like a million different triangles, so that's just like mind-blowing. And so the incenter is actually not on this line. Sometimes it is, in isosceles triangles it is, but generally the incenter will not always be on this triangle. And don't worry about it being left out there. It is still related to it. I'm not going to get into that. That should be a whole separate video because this is a very big soapbox that we could get on right now. But I wanted you to know about Euler's line because I think it's fascinating and it kind of ties all of our 6.2, 6.3 material together. Okay, so that is all I have for you. Remember, as you're thinking about, what questions do I have? Rate my understanding of what we've talked about today. Remember to rate yourself and on your understanding of the learning target and the success criteria. So the stuff we just talked about, Euler's line, that was for fun, not necessary that you understand that. So think about our learning target and our success criteria. Do you understand medians and centroids? Do you understand altitudes and orthocenters? Can you solve problems involving centroids and medians? That's what you want to rate yourself on. So, where are you on the scale? Take your appropriate action. Ask questions, help others, do your homework, etc. Now, there are quite a few practice problems that you can do to practice the skills that you have learned in this video. And, yeah. Let's end our video with a launch, shall we? Today's launch comes from Johannes A. Gartner. I hope I pronounced that right. And they say, to speak gratitude is courteous and pleasant. To enact gratitude is generous and noble. But to live gratitude is to touch heaven. I think this launch is very interesting. You can speak gratitude. You can tell someone, I am thankful for you. Express your gratitude, like verbally. And that's courteous and pleasant. That's a nice thing to do. If you show that you are thankfulness, if you show that you are thankful with your actions, that's generous and noble. But if you live gratitude, if you embody gratitude, you act thankful, you truly believe and feel thankful about everything you have and everybody you get to work with and all the opportunities that you have, when you live gratitude and you embody thankfulness, you're touching heaven. That's just the best thing. Which is true, right? The more grateful we are and the more grateful, like, we can make ourselves, like, in the deepest part of ourselves, the more we can enjoy life. So, if you want to enjoy your life a little bit more, you want to touch heaven, truly be grateful for everything that you have. The people in your life, the opportunities that you have, and, yeah, have a better life. So, that is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.